All right. Well, it's 1 o'clock. So my name's Eric Brew. I'm going to be presiding over this session. It's both a sad and exciting session. I'm glad to have you guys doing this. I think it's so neat that you organized it because Wendell was such a nice person. So our first talk today is by David Webb, and I'll let you introduce it.
All right, thanks. Well, I thought of talking about models as tools is not something I've ever done before. All of my time spent with Wendell was teaching in his class and listening to him tell me about models. So in lieu of Wendell not being here, I'm going to try to give a little bit of his side of it with some examples. Just quickly, this is a picture of Wendell. He was in our department. It wasn't my department in 1970, but he was in the department from 1970 to 2005 when he retired. During that time, the academic senate felt like giving him a couple of serious awards, only give one of those a year to a faculty member. So he won the Distinguished Teaching Award, and he won the Distinguished Service Award. The fact that he's standing in front of a residence hall tells you something about how the administration felt about him, too. They decided that Student Residence Hall would be named after people who were important in undergraduate education, and when they picked 4 names for 4 new residence halls, Wendell was one of them. Most of what I'm going to say, almost all of what I'm going to say, and probably the rest of much of what you hear today is going to be about, is Wendell's work in a series of introductory physics courses for bioscience majors at Davis. The first one of those was offered in 1995. Those courses still exist, so they've gone through the first and second generations of faculty who were in charge of them or who taught them. And Wendell worked on those even after his retirement until he passed away in January of last year. A quick outline of my talk. First of all, my view of models, I guess. My background in using models was as a physicist for many years. I taught the course that Wendell developed, but I was doing physics research for a long time, and only recently spent more time talking about models with Wendell models in teaching rather than models in doing physics. So first a little bit from my point of view. Then I want to point out that word CLASP that Wendell and collaborators came up with for his course stands for collaborative learning through active sense making in physics. So I think the active learning, of course, is a big part of it. Wendell was a big constructivist, but sense making is what I want to spend a little bit of time on, in particular connecting to models, really explicitly using models and using that word models. And also examples of what that means. What does it mean in this particular series of courses that Wendell developed to use models, for students to learn models and use those models? So that example, I hope, will tell you what Wendell was up to. My earliest physics research was on disordered magnets. It's one of the first things I worked on. Disordered magnets, because of disorder, were really hard for anyone to calculate anything. There were weren't a lot of predictions around. We were making really strangely disordered things. There are all sorts of different magnetic systems that can be disordered in different ways. And there was one particular model. Sherrington and Kirkpatrick introduced a model of a spin glass. If you disorder a magnet enough, you can turn it from an ordered state into a glassy kind of state. But still has a transition. And so they had a way of using a really simple, everybody knew in some sense it wasn't true, but a really simple way of thinking about that system. And even though they couldn't solve very much, that model gave us a language. Suddenly we could all talk to each other in a language of distributions, of couplings, and whatever we needed to do. It's a language that everybody understood, and terms were defined enough that it made sense to us. And we could talk a lot about our own work. So we could organize our thoughts using that kind of language about the things we were measuring, even without any calculations. So that's my first view of what models are good for, and it turns out in my view in education is that's one of the major things there is. Of course, other people tend to think there's a standard way to think about models is that, well, they allow you to calculate something. Of course, that's also true. There's plenty of models where there are predictions. And so, I don't know, somewhere along the line I've seen those too. Predictions that you can compare to data, and you have data and you can check those predictions really well. But I'm going to use these two ideas to think about and talk about how you use models in education. So I said Wendell was a constructivist. Chuck asked me to try to emphasize that one because he really was. Wendell really wanted his students thinking 100% of the time that they're at work, not trying to remember something. Not most of the time trying to figure out what plug do I put in here and how do I hook this up, and not those kinds of things. He wanted them thinking about physics. He wanted them making sense of the material that they had to think about, to the point where his view of how you write student activities is anything that slows them down or keeps them from doing that should be left aside. And you should focus on keeping everybody focused on making sense of the material. So Wendell wanted his students, I don't know how successful this always worked out, but he wanted them to be constructivists. He wanted them to know that they were in their own heads, making sense of these things and constructing the ideas. If not theoretically constructivist, at least practically. Practically is almost all that counts. So what happens in one of Wendell's courses? The set of activities tend to have several hours of small group discussions, small groups of 4 or 5, sometimes 6, but that becomes a problem. Learning what I would call, I guess, a language, including pictures, graphs, equations, that allows them to organize their thinking in applying models to fairly complicated situations. So another thing Wendell was about is let's not just simplify a problem and give students the simplest problems. Let's let them learn to simplify some of the problems as necessary. And so after doing a lot of thinking and really organizing their thoughts and knowing what they were talking about, they could then be prepared to do some sort of calculations, some fairly complicated calculations, that could be compared to experiment, which is what people tend to think scientists do, and is, in fact, what scientists do, because all of these models have to be grounded somehow, some way. But not necessarily the very first thing that you do. The first thing is a little bit explore and understand, I guess. So I want to give you an example. And the simplest way for me to start, I think, is right at the beginning where students start in one of his courses, and that's with what you could call conservation of energy and what Wendell called the energy interaction model. So the important thing, I think, is that this model shows up and is given to the students in a fairly complete form. Not all the energy is defined, that comes later, but the idea is there right at the beginning, that energy is conserved. You want to talk about conservation of energy, and you want to talk with other people, to other students, you really need to know, everyone has to have in their mind this physical picture, the physical system that we're talking about. What thing are we talking about? This water, or this water plus a Bunsen burner, plus the air around, or whatever. Whatever the definition has to be there fairly quickly. What are we talking about? Energy conservation is about changes in energy, so there has to be an initial state and a final state. Those have to, before you can start talking, those have to be decided somehow, before you can start talking in a way that everybody understands, at least. And then when I say the whole model is there, the change in the total energy between these two times is the net energy transferred in or out. That's basically conservation of energy. Could be work or heat. Heat in this course comes first, and even though the word work sits there, you basically ignore it. Work is the energy transfer that's not an energy transfer because one thing is hot and another is cold. That one's heat. Everything else is work. Leave work until a little bit later. On the other hand, once you start here, you can add new forms of energy. So you can talk about different kinds of energy as the course goes on. So, what language do you use to talk about things? How do students talk about things when they don't have a bunch of equations, when they're calculating something and getting an answer? And Wendell, and I have no idea how all this showed up. It was all given to me when I walked into a course once. Chuck probably knows more about it than I do. They developed some diagrammatic techniques for students to talk about the problems that they needed to talk about. So the example I want to give you is energy interaction diagrams for the energy interaction model. In fact, maybe I'll take one step back and remind, because I wanted to say that change in total energy is equal to the net energy transferred in. The net energy transferred in is due to interactions. And so on one side of the equation is interactions, and on the other side is energy. And so there's the energy interaction model. It's like Newton's second law, which has one side is forces, that's interactions. One side is the change in motion. And so it's really analogous to Newton's second law in that sense. And so energy interaction diagrams are the diagrams that students built on their own for a problem that we gave them. First example, I'm going to build this one for you and then throw up a couple more complete just to let you see what different situations look like. Suppose you want to heat water from room temperature up to the boiling point and it stays liquid. So what physical system are you talking about? Well, the water. We start bringing in other things, it gets more complicated, and all we really know about is the water. So it makes sense to identify the initial and final states as the liquid state of water at room temperature, say, and the final state at the boiling point. What you see from this problem is that the temperature has gone up. And so this energy interaction diagram has energy systems drawn as little circles. The fact that the temperature goes up is an indicator that the thermal energy, whatever you want to call it, the thermal energy has gone up. And so that's the energy change that's happened. The standard routine here was to draw a dotted line around whatever energy systems you have to show you that it's an open system. You've transferred heat in, and in fact, you can draw the arrow and say, I've transferred heat in. So a complete description is that the thermal energy went up because the temperature went up and heat was transferred in. So you can use this picture to just write down a generic equation, whether or not you know how to plug in values, heat capacities, and whatever else. You can write down an equation for energy conservation for that problem. So students could think about all sorts of problems diagrammatically without calculating anything. And so when I say they spend several hours working on this kind of thing and organizing their thoughts, that's what I'm talking about, doing this kind of thing. So, just two quick examples of how it can get more complicated. Suppose you boil the water. All right, you started out with water at room temperature. You still went up to 373, still went up to the boiling point with the water liquid. So the thermal energy still went up just the same. And then you kept adding heat and turned it into a gas. And so you end up in the final state over there with a gas at the boiling point. What happened when you turned it into a gas? Well, you were adding heat, so that some energy was going up. You know what was happening. You were busting up a bunch of hydrogen bombs that were holding the liquid together and changing it into a gas, which didn't have those bonds. So, what do you want to call that energy? Well, you can call it the bond energy. The bond energy went up. You broke a bunch of bonds. You have to add energy to break a bond. The physical system was the same. The equation, generic kind of equation, even without pasting any latent heats or anything in, is easy to write from the picture. The description, the work they do in writing down the picture automatically leads to an equation. You don't have to memorize an equation, it's just there. If anyone has any questions, by the way, you're welcome to stop me if I don't think I'm going that fast, but okay. One more slight complication, a little trickier kind of a problem. Trying to make it not too complex. So let me say I have a bunch of cold salt that I just pulled out of the freezer, and I toss it into ice water. At 200, ice water sitting at the melting point of water. And I throw salt in, and I wait a while, and the temperature goes down. So now it's 10 degrees, something like that, colder than it was. Temperature went down, then the thermal energy, thermal energy went down. The thermal energy went down. How did that happen? How do you talk about this thing in this energy conservation language? And if you're careful, if you're looking, you'll notice that ice is melted. Some of the solid water has turned into liquid. Some of the ice is melted. How do you melt ice? Well, you break bonds. How do you break bonds? You have to add energy to it. So you can say, well, okay, the bond energy went up. I can tell because there's more liquid than there used to be. The amount of liquid went up. So the bond energy must have gone up. It's a thermally isolated system. I put it in a thermos to do this. And so there's a solid line around the whole system to show you that there's no energy transferred in or out. But students can see that what's gone on here somehow is that you have broken bonds. You had to add energy to break the bonds, and that energy came from thermal energy. Now you can be sophisticated here and say, well, you threw salt in, suddenly it's out of equilibrium, there's the new melting point, there's all sorts of things that you can say. But in terms of energy, that's what happened, and you can come to it fairly quickly. If you just look at the indicators, that's why these indicators are shown here, the indicators that tell you something. Did the temperature change? Was there a phase change? Just quickly, the previous course didn't start out with energy conservation. It started out in a fairly classic way. I've taught a course like this a whole bunch of times. And a textbook always forces you to go in this direction. It started with ideas of motion and force, Newton's laws. Eventually you get to an idea of net work, the amount of work done. The total amount of work done is the energy transfer. You can show there's a work energy theorem that tells you that within this model, the net work is equal to the change in kinetic energy. So I say within this model, because this model is a point model of a particle, Newton's Newton's laws. Newton's laws are the model. Next step, work by conservative forces. Somehow it gets changed into potential energy. My feeling is that always felt a little murky because potential energy is an energy inside the system, and work is an energy transfer, which means an open system. So somehow you've gone from open to closed, which probably means you've included more things in your physical system. The whole thing just feels a little funny if you're used to coming at it from the other direction. And then there's something called non-conservative forces, which might bug you because it sounds like things aren't maybe energy isn't conserved, but it turns out it's mechanical energy that's not conserved. Later on, the internal energy, the things that Wendell's class started with, which are thermal and bond energy, suddenly those show up later on, and you can complete a picture. I don't know how often students complete that picture after going through it in these steps, but you could. It's the way it's meant to be, at least. So my opinion is that teaching using models is giving the students a way to organize their thoughts before they get into learning calculation techniques, which is what I would say the next step is. Learning calculation techniques is a very different thing than organizing your thoughts around the ideas. Now, it seems to me, I don't know all the possibilities, but it seems to me there's two things that can be done in terms of models. One is have your students develop their own models. That essentially forces them to think through carefully, in other words, make sense of what they're talking about. It's hard to build your own model with others without everybody having defined something really carefully. So it's hard to not be doing sense making if you build your own models. It's a little harder using the way Wendell did, which is giving the students a model and having them make sense of it. That's a little harder. I'm not going to try to justify Wendell's method, but I will point out, as I think of this, as a practicing scientist, this is almost the only thing I ever did. I didn't sit around developing models. I didn't do Sherrington Kirkpatrick. My name isn't Heisenberg. I mean, there wasn't a lot of me developing models. Using models for a particular situation, yes, you could call that a particular model as opposed to a general model. But this is where my feeling is this is where practicing scientists live. And this is where ideas about what scientists do tend to live. If I hear about what scientists, normal people out there, what scientists do, it's something like this. And I spent all my life doing that. I hope I still qualify, I guess. So I've already said this. I mean, I've taught Wendell's course a lot, probably once a year until I retired. So I probably taught 40 of this more than once a year. Probably taught that course 40 times or something. It's good for students to organize their thoughts before you ask them to do complicated calculations. That's what I would say. You want them to be able to do complicated calculations? Save some time for that afterwards. How much time have I got?
2 minutes.
2 minutes. All right.
Not exactly a amount of time.
Time was allowed. What can I say? Just enough time for a short rant. No, the terminology of standard textbooks bugs me a little bit because it's all about theorems and laws. And laws, to me, sound like things that are true. On the other hand, and theorems sound even more like things that are true. But it's a theorem within a model. All the theorems that people prove are based on some sort of model. If the model's junk as far as physics, the theorem may still be beautiful and correct and a great thing. But it's not very useful to us to pay any attention to it if we're physicists and that's all we care about. We don't care about beauty. Who knows? I get the feeling that students think of laws and theorems more as truth. And the idea of using the word model I like a lot because it tells you that it's an invention of a bunch of humans And it's not a piece of what the world is, it's our way of viewing that world. And I think the word model helps do that. All right? Jen.
So we have 5 minutes for questions.
Yeah.
There's another perspective on laws and theorems versus models. In the way I teach it, the laws and theorems are the framework that defines the kind of terms that you want to put into your models. So that Newton's framework, Newton's laws, Newton's principle tell you that when you build a model, you talk about objects, you talk about interactions, and then how those interactions and objects respond are controlled by what the framework is. It's like evolution, where evolution gives you a framework that doesn't tell you anything. But if you want to figure out how are these species related, now it tells you what to make hypotheses about and what kind of model to build. So it makes the laws and theorems a little stabler, and in particular for this population of biologists who tend not to have anything that they can really hold on to everywhere, it's very nice to show them Newton's laws that work for everything from a molecule to a galaxy. And Julia's going up next, so she can respond.
I guess my only response would be that within Wendell's model, Newtonian model of particle motion, or whatever he actually called it, I can't remember the exact terminology, he did call them Newton's first, second, and third law. So, I mean, it is the world we live in, but yeah, framing them in some way that
I love the model stuff. I mean, it really is.
Tells you that it's not
I'm transformed to this too, but I do keep the framework.
Other questions?
I don't have a question. I have a response to Joe.
Yes.
And you know, it's funny because I was looking all through my computer just for evidence of my interactions with Wendell, and I stumbled across an audio recorded conversation between him and I where I was complaining to him about you. And I was so frustrated. And I was saying, he just won't let go of this idea about laws, and I don't understand why. And I don't understand why he wants them higher up in the epistemic hierarchy than models. And I was going on, and Wendell basically said something like, you know, it just doesn't matter what you call things. We have a bunch of ideas, and the reason not to use the word laws is just to not, what you said, just to confuse students into thinking that we know things for absolutely certain. And we can call things frameworks or theoretical frameworks or other things, but that was his main message, really. Like and as you'll see in my talk, he's just such a pragmatist. He's just really about what's going to make sense to students, and who cares about what the formal definition of things is.
That's right.
Touche.
All right. Questions? Other responses to Joe? All right, well then.
Oh, wait,
Chuck has a response.
It's just Joe. We need to.
more Beatles.
All right, well then, Julia has promised that she has a 3-minute stand-up routine. Burn the time, but why don't we go ahead and thank David